hold it like a... Okay, it's not going to work. Right. Okay, so what I might do is begin. Welcome to this experiment in remote or webcasting. This is a lecture to cover an introduction to the Archer service, or the Archer system, as from Cray's perspective, and also a guide into how Hector users might transition through to Archer. I've been asked what the structure will be. The aim would be this first portion will run for about an hour, so we will break around about 3 o'clock, and we'll start back up again with probably another hour around 3:30. This first section will be much more on the hardware and what fundamentally makes up a Cray XC30, and the second session will be a bit more practical for people who might, or what issues and things people should be aware of when they use an XC30 in reality when they get access. So a little bit of background. Again, probably a lot of people in this room very familiar with this as we're here in Edinburgh, but possibly across the web, maybe they're not. Hector is the UK's frontline service and has been since 2007. It is scheduled to end in early part. So that's wrong. In the early part of 2014, rather than 2013, and it's funded by the UK Research Councils and various partners, of which my employer Cray is the hardware supplier. There've been 4 phases to Hector, so even though it has been a single service, it has actually been 4 separate machines, or 4 implementations of machine, all Crays. So the first phase we had the Cray XT4, which was dual core, and we've gone through various upgrades, changed the network, until we've come to the Cray XC6 in what we call phase 3, which has the Cray Gemini network. And through each of these transitions, there have been requirements on users to adapt their codes. And similarly, we expect sort of the move between the XC30 and the XC6 to have a sort of be similar maybe to a phase upgrade that happened during Hector. So why am I talking about Archer? Well, Cray have been awarded the contract to supply the hardware for Archer. So we are going to be providing a Cray XC30 to the Archer sort of service. And this was announced not long ago, and at the moment is the only part of the service which has been contractually agreed. Cray XC30 is a brand new architecture, so it was designed it's not just an upgrade over the XC6, it's almost a complete redesign of the large fundamental parts of the supercomputer. But it also maintains a lot of the heritage and tools and interfaces that were available on the Cray XC6. So we're expecting it to be hopefully a relatively familiar environment for people moving from Hector potentially onto Archer. So what I'm going to get onto now is how the XC30 is sort of put together, what makes it a supercomputer, how people view interacting with it. So the Cray XC30 system. Just a little bit of background, maybe advertising on Cray's behalf. There are quite a few already pre-existing XC30 systems. At least 3 I can think of in Europe, several around the world, several large systems, generally based on the Intel Sandy Bridge architecture, which is a slight difference to what Archer will look like. But it's a very popular system already, and I think we expect to see it widely used at various sites around the world. So even if you're not necessarily using Archer, a lot of the fundamentals I'm talking about here apply to any XC30 system. So again, just to sort of so we're all on the same level, nodes. The Cray XC30 is a massively parallel processing system, same as the heritage of the XC6, XT line, and even the T3 E Cray lines. So what that means is it's made up of a large collection of nodes. Fundamentally, from Cray's perspective, there are 2 types of nodes: compute nodes, which do all of the work, which are actually doing the supercomputing element, and service nodes, which are there to provide all of the features that we need to make it into a supercomputer, to make it useful for users. Typically, in any XC30 system, there will be many, many more compute nodes than there are service nodes, but it's useful to sort of know that this difference just to understand how the system's put together. So individual nodes probably can't function as a supercomputer. They need to have some method of communicating. We do this via some network or interconnect, and Cray do this through the Cray Aries interconnect, which is our one of our major features of the XC30. So all of the compute nodes and service nodes in the system are connected via this Aries interconnect, and I've represented this quite schematically with this sort of all-to-all connection. And so any group of cabinets will contain many nodes, all interconnected. So none of these nodes have their own storage. Instead, what we do is we attach storage externally, either through a Lustre file system, which is a high-performance scratch file system, which is where the majority of bulk data will go, or we may project another file system, possibly say something like NFS, out to each of the nodes via this DVS server. So all in this representation here, the blue nodes are the compute nodes, which your actual work is happening on, and the red nodes are service nodes, which are providing additional services to the supercomputer. So how do users interact with an XC30? So what was going to be provided are Cray development login servers, CDLs. And these are external to the actual supercomputing system, but they provide a continuous service. Potentially, while the system is down, you could still access the CDL nodes. They also provide all of the compilers, all of the interactive development environment that you will access. So when you log into Archer, you will be accessing one of the CDLs, and there may be multiple CDLs for a single supercomputer, depending on the scale. And these use the gateway node to communicate with the rest of the service. So again, you might hear reference to a gateway node. So what actually makes up a compute node? So fundamentally, a compute node is two sockets of Intel Xeon processors with some discrete memory and then a connection to a network card. In this particular case, we'll be using the 12-core Ivy Bridge parts, which are connected using QPI, Quick Path Interconnect. And what this forms is two Newman nodes. So those of you familiar from Hector might be aware there were 4. There's only 2. And in total, there will be 8 channels of DDR3, which accessing, for the majority of nodes, 64 gigabytes of memory. There is a difference, which I'll explain later, between some nodes where they may have more memory. And each node is connected to a single Aries network interface card, or NIC. And this uses the PCI Express 3. And this is how they communicate with the outside world. So in reality, nodes don't exist on their own. They're put into blades, which are then stacked up into cabinets. So what does a blade look like? A blade is 4 compute nodes. And this is then connected to a single Aries 48-port router. So we have 4 network interface cards connected to a single router, which then is connected to the rest of the network. As I said, we're using PCI Express, which gives us a lot of bandwidth between the compute node and the network card, and various. Then what we do is we have 3 separate network ports which interconnect the Aries routers together. So we have what we call the rank 1, which is across the backplane, rank 2, which connects between chassis groups. I'll explain in a lot more detail later. And rank 3, which is an optical link which connects groups together. A fully populated blade looks a bit like this. As you can see, we've got 7 heat sinks, because one of the heat sinks has been removed, and these represent the sockets which the Intel processors sit in. You can see the memory cards. If I use the mouse here, memory cards sort of lying along each side. And then here it's plugging in to the Aries chip at the back here. From a system administrator's point of view, this is quite nice that you can upgrade these daughter cards as complete units. So in the future, if there is an in-socket upgrade or some change, maybe we move to a new processor architecture, the blades can be reused and a lot of the wiring can be reused, and all we have to do is replace these daughter cards, which basically form half. So there are 2 daughter cards per blade. Service nodes look quite similar, except they have the ability for expansion. So the service nodes, because they interact externally with extra services like Ethernet or InfiniBand, have the ability to have additional PCI Express slots. Again, they will have Intel processors attached to them, but they're not quite as dense as the compute nodes. So there is a difference in the hardware between compute nodes and service nodes, though it's not a particularly large one. So how do we group these up into a system? So the fundamental unit is a compute blade. We'll then package 16 of these compute blades into what we call a chassis, and these are horizontally aligned. Which basically gives you 64 compute nodes. We then put 6 of these chassis together in 2 cabinets, and this is what we call a group, and that's 384 compute nodes. And a group for a large supercomputer is perhaps the unit that you buy in, and then we'll form multiple groups into the size of the system depending upon how large a system has been purchased. So how do we connect these together? So once we've got the Aries, we've got this dense packing of blades and cabinets. How do we gonna push these together? So we've got the Aries interconnect. The Aries is a upgrade of the Gemini interconnect. So it has a very common heritage, except there's been a significant improvement in a lot of the fundamental features, and there is a significant change the way the actual routers are connected together. Again, it is an HPC optimized interconnect, so it is designed to transfer high bandwidth and low latency over relatively small differences, so along the size of a data center. It's not going to be used to send data across the world. It's fault tolerant, just like the Gemini, so again, if any particular link fails, the Aries interconnect has the ability to route data directly around any failure, or in fact actually active traffic management as well. So if any particular point in the network becomes congested, it can route data straight around it. Again, it's a connectionless design and doesn't require any switches. So effectively all of the blades in the system are really compute or service nodes. We're not putting switches in there to connect things together, which means that we can scale to very large numbers of endpoints. So if we look at how it's all connected together, we talked about a chassis. A chassis is 16 compute nodes. And what we do is we connect every single Aries to every single other Aries via a direct connection over the backplane. So this gives us a one hop between any particular Aries to any other Aries. So imagine how this would be mapped onto the back of this chassis. So on a first instance, the first packet of data would be sent over that direct link. However, that eventually we might start saturating that link to the point where that link is full. So what we can do is choose any intermediary Aries in the network and start to route data through that one. And we can keep doing that until we reach the full injection bandwidth of the Aries, effectively increasing the bandwidth that way. And this is all done on a per packet basis. So the routing is independent of the actual, is independent of the to endpoints. It's effectively done on a per packet basis. So we can get up to many, many, many different endpoints and all this data bouncing around the network. Rank 2, we basically copy the same idea. So we have a chassis in which every single Aries is connected to every single other Aries via this rank 1 network. We then group 3 of these into a cabinet, 2 cabinets into a group, and we add multiple all-to-all connections between each of the chassis. So effectively there are 16 sets of all-to-all groups between every member, every point in the chassis. And this is what we call the rank 2. And this is also a copper network, so it's passively, so it's electrical, and thus economical for us to implement, but also high performance. And effectively a group is 768 sockets, or 384 nodes potentially. And then what we'll do is we can interconnect these groups via the optical cables in what we call the blue network. And again, name that in a bit more detail. So how does data travel between any 2 points on the rank 2 network? So say we have a source processor that's sending data, or source Aries that's sending data to a destination Aries. What we do is we find the minimal route between these two points. And this is always done rank 1 first, then rank 2. So the minimal route is a single Aries here. So we travel first over the rank 1 network, then we travel over the rank 2 network. Now there's 3 lines for the rank 2 network because every single connection is actually 3 lanes, so it can travel over any one of those 3 lanes, but ultimately it's still ultimately only 2 hops between any 2 points in a chassis, sorry, in a group. Again, just like the original connection, we may saturate that with potentially because the injection bandwidth of the Aries is very, very high. So what we'll do is we'll choose a non-minimal route, and this basically goes up to 4 hops, but chooses an intermediate point to route data through. And this is again chosen randomly on a per packet basis. So here we're choosing this R processor. We're finding the 2 minimal routes now between this point and the destination. So we find the minimal route between the source and the R, which is this processor here, this M. We're always routing rank 1, then rank 2. And then we do the same from the R through to the D, rank 1, rank 2. So any group 2 network has sufficient bandwidth to support the full injection rate of all 384 nodes when they're using the non-minimal routing. And because there are so many links in the system, because of this all-to-all topology, or hierarchical all-to-all Dragonfly topology, there's huge amounts of bandwidth available. And there are very few congestion points within the network. So once we've created a group, we need to connect the groups together. And this is done through the optical network. Obviously, optical networks being very high bandwidth, and the cost does scale. So up to 240 ports, so basically up to 240 Aries connections are available to be connected between each cabinet group. The global bandwidth can be tuned, so customers can choose to buy or more bandwidth between individual groups. But we start with a sort of default level. I think that can go up to 4 times longer, so these bundles. As you can see here, they sit on top of the cabinets and generally sort of become quite a wiry mess. Again, we have adaptive routing between cabinets or between groups over the blue network. So we all-to-all connect all of the groups, so every group is directly connected to every other group. So we have a minimal path, but that potentially may become congested. So we can choose any intermediate path or all of the intermediate paths to send our traffic over. And again, this doesn't affect latency, because latency is always the first packet, which is usually done by minimal route. It's only bandwidth that you're enabling by using non-minimal routing, or including bandwidth. So every job has access to the full system bandwidth. So 3 things, or the 3 networks to be aware of: the rank 1 network, which is the intra-chassis network; the rank 2, which is the intra-group network; and the rank 3, which is the intergroup network. And the idea is, by separating them out in this way, we minimize the amount of active optics that are required, which are very expensive and make machines expensive to sell and expensive to buy. And we maximize the use of electrical signals like copper and backplane routing on the PC board. In the past, if you've ever seen a presentation by Cray, it might have been that we referred to these networks by color. That has fallen away as we've actually implemented the system. So in the past, what might have been called the blue network in this particular diagram is green. So you can see here that the green cables are the optical cables, which are leaving the top of the cabinet. But the copper cables are just connecting between those 2 groups. And once that's wired in, the group is totally, you never need to really change that, even if you expand the system. all you need to do is add additional cables via the active optics. Again, if we see, considering the number of connections, someone who's less au fait with the hardware, who doesn't deal with hardware very often in the sense of actually having to wire it in, might say that's a lot of cables. However, considering the number of cables, it's actually very tidy. So why is the Dragonfly topology good? So this entire topology is what's called the Dragonfly topology. It scales to very large systems. So you don't sort of, by having these tiers of all-to-all, you don't end up kind of with billions and billions of connections to every other point. But it also gives you this, this very good performance. And the Cray Aries NIC and the router are actually doing quite a lot of adaptive routing and using algorithms that have been developed in conjunction with academia. And it's also designed to smoothly mix small and large messages. So if you're doing very small messages, low latency traffic, it can also travel on the same network as the high bandwidth transfers, say all-to-alls, that kind of thing. Again, it's implemented without external switches, which means that you don't have to waste space in your cabinets or power these. All of the routing is done on chip, so it's all part of the network. And it effectively hopefully makes us competitive with giving the best value to customers. So if we go back and we look at, again, how these groupings happen, the compute blade, that's not, like, individual compute blades aren't connected or connected via SIM. Via the Aries. The chassis is effectively the part of the rank 1 network. The intergroups is rank 2, and sorry, the intragroup is rank 2, and the whole system is connected via these active rank 3 up to optical connections. Does anyone have any questions at the point? No questions from the room. There may be hundreds on the webcast, but we have no way of knowing. Storage. So Cray uses the Lustre by default, Lustre file system as its way of providing high bandwidth capacity storage. Individual Lustre clients run on each of the compute nodes, on the service nodes, and then they connect via the Aries network, either through the LNet routers to the back end, which are object storage servers and object storage targets. So effectively, what you have is very highly parallel writes to many disks, allowing you to get good system bandwidth. So this is fairly common in a lot of our applications. We use, or in Archer certainly, we're going to use the Sonexion, which is a Cray branded storage unit or storage, which contains a combined object storage server, which is the intelligent sort of server, and metadata management unit, which is the MDS, the metadata server, all in a single sort of rack, which can be just rolled in and plugged in. And basically, effectively, the bandwidth scales with the number of SSUs that you have. So if you need a certain bandwidth, you plug more SSUs in. Power and cooling. Again, probably not actually of direct relevance to users of Hector and Archer, but it's certainly very important to the run maintainers and people who run these services. Also potentially of interest to all of us, because the less power it draws, the less it costs to run. In this particular system, the XC30 is switched from, so in the XC6, air was blown from the bottom up through the cabinet. In the XC30, we now do transitory cooling? No, transverse cooling, sorry, transverse cooling. So effectively, cold air is blown from the room across a group. It comes out hot, goes through a radiator, which is then cools it, or the opposite of a radiator, heat sink, which is then actively cooled, and the air is then passed again similarly through this way. And this allows us to be effectively room neutral. So all of the heat is pushed out into the cool water, which is provided by the site. So we have this vertical water cool. So yeah, power is provided as a single unit per cabinet. We have a blower cabinet in between each group, and then we have the independent compute chassis. And the advantage of this, of having cooling sort of separated from the compute units, is very useful for maintenance. You don't have to involve yourself with plumbing when you try and replace a compute unit, and it keeps everything separate and everything working and everything reliable. We also actively cool the active optics through some of these connections. Again, so there's a lot of effort and design has gone into designing the heat sinks and the way this cooling happens. I think a significant proportion of the R&D budget goes on how to make these systems dense. So if you compare the size of systems, they're gradually shrinking. If you look at, say, even just Hector, we went from, on the order, I think it was 60 cabinets on the XT4 down to 20 or 30 cabinets with phase 2B and phase 3, yet significantly increased the compute capacity. So if there's a trend to sort of shrink these down to as small as possible to get the best, what they call PUE, or power, basically the ratio of power to cooling. How this might actually affect users is there's now features to monitor how much power is actually being used by an individual application. This could either be used at the site level, just as a general interest, or possibly at the job level. So it may be in the future that rather than requesting time for your application, you request power. It's not quite at that granularity yet, but it certainly is information that you can get out of the application just from the operating system. So one of the features that might be useful is if your site can only draw a certain amount of power and you've installed a computer that can draw more power, you can limit how much power is drawn at any particular time. So if your theoretical peak is higher than your actual sustained peak, you can control this through some kind of scheduler. And this will see more and more important, I believe, in the future, and we'll see more and more control over this as we upgrade the software. The hardware is there, but the software still needs sort of exposing. So what does Archer today look like? Archer is currently installed. At the moment, we have 8 groups, which is 16 cabinets, which gives us 3,008 compute nodes. Strange number, I know, but let's see. Of those, we have one group which is entirely configured with 128 gigabytes per node, so double-sized nodes. And the rest are 64 gigabytes. We have 32 of the service nodes that I was explaining, and we'll have 8 Cray development logins with 256. They each have 256 gigabyte memory available. We'll also have 2 pre- and post-processing servers, which I believe might be a terabyte. I'm going to take responsibility and say I may have misrepresented that. I'll check, but it's a very large amount of memory available on those pre- and post-processing servers. And we're going to back this with 20 SSUs, so that gives us 160 Lustre object storage targets, so potentially 160 places to stripe your data. And those are going to be distributed into multiple file systems. And as yet, that hasn't been decided how those are going to be configured. That will be, when the service provider is announced, that will be their decision. But we're getting sort of on the order of 4.5 petabytes of storage available. Again, distributed between different file systems to prevent interaction. So, sorry, just look at the time. So, yeah, again, a lot of the figures, we only recently announced Ivy Bridge as a component available for our XC30 systems. So some of the data that we have lags what we have. What we do have is quite a significant amount of data for Ivy Bridge, which is the previous generation of Intel. So all I can say really here is that you expect Ivy Bridge to be quite a bit better, but still you can see that moving from XC6 into Lagos to XC Sandy Bridge, we're not seeing, even though the peak for HPL isn't improving significantly, we're seeing a lot of the other figures improve significantly. So things like stream, memory bandwidth, again, that's, well, actually, no, sorry, random ring latency, that kind of thing, point-to-point bandwidth significantly improved. And these are a lot of features of the network. I think I've got other benchmarks which show that the nodes themselves are actually significantly more powerful. Latency, lowest latency is just to do a put, because you don't have to communicate with anybody, or you can just fire and forget almost. MPI is slightly more complicated because you've got the effect of message matching, so you've got to have some active involvement of the CPU. And GET obviously is effectively twice the size of PUT because you have to do a request and then someone has to send it. But still we're seeing on the order of microsecond latency, sub-microsecond for some components. And this is an improvement over Gemini. It's not orders of magnitude improvement, but a lot of latency is dependent on physics and the fact that systems occupy space and bandwidth. It's bandwidth where we're seeing a significant improvement in topology. So again, here we're seeing up to sort of 14 gigabytes per second bidirectional bandwidth between nodes on the system as we increase message size. And again, it's twice what you sort of, if you send in just one direction, you can send and receive twice as much data than you can just send or receive. Message rates, which again, very important to things like PGAS applications, the number of nodes that you can, or the number of messages that you can put in a particular number of rate at which you can put things, again, sustaining millions upon millions and millions of messages. One of the core features, which I think I failed to mention in the Aries introduction, is there is support for hardware collectives of relatively on relatively small chunks of data, so things like hardware barrier is available and hardware all reduce on sort of single word transfers. This significantly reduces the latency compared to software. So here we can see how the collective offload, we're getting under 10 microsecond latency on 126,000 processes. So that's a significant improvement over software, sort of on the order of magnitude. But again, it only applies to quite small reductions, and it does require additional options to be passed to the library when you compile your application, which I'll go into later. All-to-all bandwidth, this is where a topology like Dragonfly really shines. Again, it will scale the system. So this is taken directly from Archer when it was in the factory in Chippewa at the Cray factory. We can see that we're getting on the order of almost 7 terabytes per second when we get to reasonably large message sizes. So again, obviously that scales with the, as soon as you get over a certain threshold, you're reaching significant all-to-all bandwidth. The more endpoints you have, the larger your bandwidth. Again, this data from Sandy Bridge, but again, it applies probably more so to Ivy Bridge. Compared to Interlagos XC6, we're seeing that between sort of 1.5 to almost 3 times an improvement on per node performance. So depending on the application, depending on its particular needs, but these nodes are significantly more powerful than the XC6 nodes. And we're seeing, and this will be even more so with Ivy Bridge with more cores and more memory bandwidth. MPI bandwidth obviously maps directly with, similarly to the PUT bandwidth, because effectively that's ultimately what it is. And again, we're seeing up to sort of 16 gigabytes per second bidirectional bandwidth when you get to the larger regimes. Nice, relatively smooth curve. Few points where we switch between regimes, so we switch between Rendezvous and Eager protocol at 4K, and again, it flattens off as we sort of saturate the network. So more information, actually then, apologise, that took a fair bit less time than I expected. Further information that you might want to look at, the Cascade Networking white paper is extremely interesting, goes into a lot of fine detail as to how the topology works, how the Aries works, perhaps more for the very interested, or there was the SC12 paper from last year. So are there any further questions or any areas where I could go over that in more detail? Question in the room? Yes?
How does the latency change depending on how many networks you have to go through?
So the question was, how does the latency change compared to the number of networks that you go through? So if you imagine with a mesh network, the number of hops can grow quite, can get very large quite quickly, especially on a large system like, say, Hector or even larger blue waters. And that, obviously, the latency scales with the number of hops. The number of hops that you have in Dragonfly is relatively small. I think I should know this off the top of my head, but I have to think about it every time. Into cabinet, the minimal route is effectively 1, because you could be on a direct connection between 2 points. The maximum minimal path is 1, 2, 3, 4, 5, I think. Yeah, that's the minimal path. And effectively the difference, once you're on the network, the hops are actually very short. So, I mean, it shouldn't affect the latency a great deal. You will see lower latency, obviously, between processes on an individual node, and you'll see a lower latency between nodes that are on the same Aries. So we see that on